servo systems. So it is nothing, we are going to controlling a load that is called a servo system. In this we could control the output in positioning the motor or the direction of the rotation and the speed. So the it is classified into two types. One is DC servo and AC servo system. In DC servo, we are going to have a DC signal. So first we will have an angular position as input. So there will be an error detector, then an amplifier, then you will have a DC power amplifier, then DC servo motor, then the output. So from the output, we are going to give back to the error detector such that it will detect the error and accordingly will give the input to the DC servo motor. Okay, I'm going to replace it. Okay, so I'll just explain it. So let me given I need an angular position of theta 1, it may be 60 or 70 degree. Now what happens, I'm going to switch on the DC power supply, the motor rotates. It is going to measure me theta 2. So the theta 2 is given back to the error detector. The error detector will have the difference between theta 1 and theta 2. So the amplifier amplifies it and give it to the power amplifier. Then the DC motor rotates accordingly till it get theta 1, it will be sensed. Okay. So this is DC servo motor. Now we have two types. One is armature control and field control. I have drawn the circuit. Now Vs will be the supply voltage, field current, field voltage. Now let me have the field resistance, field inductance, armature voltage Va, Ia armature current, armature inductance, angular displacement, moment of inertia, and B nothing but frictional coefficient, back EMF, then the torque constant. Okay, so T is proportional to Ia and uh, Eb is proportional to omega. So Eb is equal to Kb omega. Now here first one, let us see the armature control. So I'm going to have only the armature. So if I'm applying the KCL, I could write it as Va equal to Ra into Ia, La into dia by dt plus Eb. Okay, take the Laplace transformation. You will be getting Ia of s Ra plus Las into Ia of s plus Ebs plus Vas. Okay, so now you know very well Eb equal to Kb into S into theta S. So T is equal to J into d square theta by dt square plus B into d theta by d theta. These two are nothing but inertia and frictional coefficient. So after taking their Laplace transformation, I could write the same thing as this one. So Ia is nothing but Ja square plus Bs plus theta of s. And Ia is also Va minus Ea divided by Ra plus La. So now substitute everything. So I'm going to substitute it. So let me substitute, instead of Ia I'm going to substitute J square. Instead of Eb I'm going to substitute Kb in S theta S and Va of S. So theta by Va of S is nothing but Kt divided by the denominator. So this is the transfer function for armature control. Now we are going to draw the block diagram. So here we know this Va of S. Okay, so Ia of S is nothing but Va minus Ia into 1 by Ra plus La. So I'll have an error detector. So I'm going to give the input as voltage is input. Eb is the back EMF which is measured from the your output. So my motor. So only I'm giving in the negative. Then it is given to the block such that I'll be getting Ia, which is nothing but 1 divided by Ra plus La. So this is the first block. Next, Eb equal to Kb into d theta by dt. So I could write it as theta into Kb gives me Ebs. And also you know that Ias is equal to 1 by kt into Ias equal to Ts. Okay, again we know that Ts into the transfer function gives you theta of s. Okay, so this is the blocks. So I'm replacing all the blocks. First I'm replacing Ia and T, the block is Kt. T and theta, the block is 1 by J square S, J square plus Bs, and then I will have my KBS like this. So this is my block and the transfer function for your armature control. Next, we are going to see the field control. So I'm going to have my field control. So this is my equation, that is RF plus LF equal to VF. So this is my IF of S. So IF of S equal to VF of S 1 by RF plus LF. So 1 divided by RF plus LFS, and also you know that T is equal to Ka of S, and also J, the inertia and the moment of inertia, 1 by J square plus Bs block will be there between the torque and the theta. So combining all the torques, after Vf you will have your 1 by Rf plus Lf, then Kt, then 1 by J square. So theta by Vf, just all the blocks are in cascade, multiply it and write it. So this is the field control system. Now we will move on to the AC servo systems, which is having an AC signal. So after the angular position, you will have the AC error detector, AC amplifier, AC power amplifier, AC motor. Now I will have a feedback. So now I am going to replace it with everything. Now the system has a rotor and the control winding, and I'll have a reference winding. I'll have an amplifier and a modulator in the control winding, which will give the control to the reference winding. So here EC is the control signal, TM is the torque developed, loud torque, theta angular displacement, and B is the frictional coefficient. So tau m is equal to Kc into EC minus K into d theta by dt, and also Ti is equal to J into d square theta by dt square plus B into d theta by dt. At equilibrium, we could write it as motor torque equal to load torque. So I'm going to equate all the things. So write motor torque equal to load torque, take the LCM, sorry, take the Laplace transformation, find out theta by EC. So you will be getting like this. So theta by EC, just take the common terms outside, that is B plus K I am taking outside. So you will get like this. So motor gain constant is given by Kc by B plus K, and motor time constant is given by J divided by B plus K. So this is my final transfer function for AC servo system. Now the next one which we are going to see is synchros. Synchro, which is a type of a transducer which transforms the angular position of a shaft to an electrical signal. So from the position we are going to develop the electrical signal. So this is I have shown you the synchro transmitter. So the first one which we are going to see is synchro transmitter, which will have a rotor like this, and then surrounding it you will have the three-phase stator winding. So in the synchro transmitter you will measure only the stator voltage. From the stator voltages we are going to measure the rotor position. So let me measure between S1, S2 and S2, S3 and S1, S3. Okay, like this. So I'll have ES1 as a reference. So ES1, ES2, ES3. So all the voltages will be 120-degree displaced. That is what I have written here. So ES1 S2 is equal to ES1 minus ES2. So applying the cos function, cos of A minus B, I could write cos A cos B plus sin A sin B. So cos 120 you know very well, it is cos of 1 minus 1 by 2. So cos theta 3 by 2. So take root 3 outside. So you'll be getting sin omega t root 3, and then just convert root 3 by 2 as sin 120, so that finally you will be getting as a sine function like this. So this is the final function. So when I'm with the help of this formula I could determine the position of the rotor. ES1, ES2, ES3 is given by the 120-degree. If the rotor position is taken as the electrical zero position, by measuring the stator voltage, I am going to measure the position of the rotor. Okay. Now coming back to synchro control transformer, again you will have a rotor surrounded by the stator. Here I am going to give a generated EMF as the input to the control transformer. Okay. So rotor is connected to the load. Rotor EMF will be measured. Okay. Now the next synchro which we are going to see is synchro detector. It will act as both, but that is, it was a combination of the transmitter and the receiver like this. Okay, the transmitter and the receiver. Okay, so here if you see, the rotor here will be rotating, forms the flux. Okay, so here which will energize the the next side rotor. Okay, so then what happens, it will, if the rotor rotates here, it will give the signal, and the same like the rotor rotates and that load is rotated, and the conditional unit gives back the signal. So this is your synchro error detector. Okay. Next, we will see your multivariable control system. So the next one, it is a multivariable system. So we have seen single input and single output. Now we are going to see multi-input and multi-output. So variable or interacting and non-interacting variables are there. So interacting, we are going to call it as coupled, non-interacting decoupled. So interacting variable, name it as u1, u2 as the input, y1 as the output, and g will be the transfer function between the input and the output. So I could write my equation as output equal to input into transfer function. Now suppose m is equal to 3, in the sense you could write 3 cross 3 matrix and the equation will be written like this. Okay, so if I'm talking about the interacting variables, so whenever I'm having this, that is the coupled variables. So from u1 it goes to all the g11, g21 and g31. Again, I could write this as G2 also G12, G22, G32, G3 also U3 also G31, G32, G33. So now I have written everything. Now what, from Y1 you could see that it is G11 Y1, G22 U2 into G12, G13 into U3 over. Now when I am talking about Y2, it is nothing but G22 into U2, G21 into U1, G23 into U3. Now Y3 is nothing but G31 into U1, G32 into U2, G33 into U3. So these are the complicated. So what we are going to do is we are going to decouple the variables. Okay, so we are going to decouple it, which becomes a non-interacting variable like this. So I could write it as which is not having any connection, or simple block you could write, and then we can couple it again. So this is called as MIMO system. So here, so which is not interacting with each other. So I could write it as GC1, GC2, GC3 as the control function, and I'll have a separate feedback from all the output to the input. So it is not interacting, and this is your multi-input and multi-output system. Thank you.